So why are corneal biomechanics important? Sven talked about coming into a brand new world, but corneal biomechanics were important long before the Corviz was actually introduced. But is it just scientific curiosity? The Corviz allowed scientific curiosity actually to move into the clinics so that more than just the scientists could be involved in learning about biomechanics. Keratoconus detection is really the first application that was chosen for obvious reasons. It's extremely important in refractive surgery to avoid operating on subclinical keratoconus. So it was really the first thing that was developed. One can also look at the development, progression, and treatment, as in corneal cross-linking of keratoconus with biomechanics. Because really the first detectable change in keratoconus is likely biomechanical. We can identify patients at risk for iatrogenic ectasia after surgery, and it's extremely important in accurate measurement of intraocular pressure. After refractive surgery, I gave a talk today in Hanato's course that after refractive surgery, applanation tonometry is completely worthless. So if you want details on that, we can talk later because that's not part of tonight's program. And there's new ideas actually in the development and progression of glaucoma that we can start looking at biomechanics relative to that as well. But how can we actually measure this clinically? The Corviz ST is an air puff tonometer that has many additional features to it. So it's like an air puff tonometer in that it uses an air puff to deform the cornea. That is the non-destructive load that allows us to look at the response to that non-destructive load. It has a constant air puff. So when you compare parameters from patient to patient, you know they've all had the exact same load. So it makes the comparison much easier. And it's of the horizontal meridian of the cornea. The motion that happens, and I'll show you in a minute from Corviz exams, but what I want you to know that is measured, this blue line is apex displacement of the cornea. The green line is whole eye motion, which is measured in the periphery. So those are the two measured parameters. If you subtract whole eye motion from apex displacement, that produces the red line, which is pure corneal motion. It's called corneal deflection. So the red line does that. But now here, this gray dotted line is the air puff, and here's the maximum air puff. But look where the maximum cornea motion happens. It's before the air puff. So the cornea comes down, reaches its maximum air motion, but the air pressure is still going up. So the whole eye starts moving backwards. As the air pressure turns the corner and starts to come down, look what happens. The cornea starts to recover, but the eye's still moving backwards. So it goes backwards until the cornea is fully recovered, and that's the point where you have maximum whole eye motion. So this sounds very complicated, but it's actually provided many new research areas. And for me, next year, maybe I can tell you how we can evaluate scleral properties relative to corneal properties, and that may be very helpful in glaucoma. So this shows you what I meant. This blue one is an undeformed cornea. Now watch, here's the temporal progression on the side. Here's how whole eye motion is defined. It goes from blue to red, which is the maximum corneal motion here, and white, which is maximum whole eye motion. Now I took this particular exam out of a data set of 700, and I took the maximum whole eye motion of all the eyes in the data set. So this is the maximum it would move. Other eyes were much less than this. Now if you overlap all the peripheries out here, it gives you pure corneal motion. And then you have lots of parameters that you can extract from these data. So the Corviz parameter classes, there's multiple events, such as first applanation, highest concavity, second applanation, and maximum whole eye motion. And for each of those events, associated with them, you can get an amplitude of displacement, timing, anterior corneal velocity. Those were some of the first parameters that were put out. But the really important for corneal properties, for corneal stiffness, have to do with the shape of the cornea, not the amplitude of deformation. And the shape of the cornea is provided by highest concavity radius, which is the radius when it's in its maximum state, the curvature it has when it's most concave, and deformation amplitude ratio, which is the ratio of the central deformation to a point 2 millimeters out. And the two sides are average, so it's a shape, central over peripheral. And then integrated inverse radius, which has actually been shown to be extremely sensitive to picking up differences in biomechanical states of corneas. And this is actually curvature, because they didn't want to call it curvature because then many clinicians expect diopters. And diopters don't make sense here. So inverse radius is curvature. To get power, you multiply it by difference of index of refraction, and that gives you diopters. So this is just curvature. And it's integrated area under the curve between the first and second applanation. Very sensitive parameter. So IOP versus properties. The amplitude, timing, velocity, these are all much more sensitive to IOP. So if you look in the literature and you see two groups compared where one has greater amplitude deformation than the other, that means that group has lower IOP than the other. And if you think about it, non-contact tonometers would have not worked all these years if the most important influence on deformation amplitude were not IOP. So if you look at then the shape parameters, they're much more sensitive to properties. So that's how you can actually separate them in your minds. What I'm showing here is of a single exam. We have the anterior edge of all the exams. So you can see applanation happens very early in the air puff. And if we use that as our reference for load, because that's where IOP is measured, we can look at two different displacements, either from undeformed to applanation or from applanation to highest concavity. So if we want to look at the stiffness, if we look at the corneal stiffness, we want the load from undeformed to applanation. So that's stiffness parameter A1. If we want to look more at the scleral response, we look at the displacement from applanation to highest concavity, and that gives us a separate SPHC, stiffness parameter. We use the biomechanically corrected IOP developed by Ahmed El-Sheikh and his group to come up with the load. So we get the air pressure minus the biomechanically corrected IOP. And then we look at where in the air puff applanation occurs. If it occurs earlier, the air pressure is lower. If it occurs later, the air pressure is higher. So we have to know when it occurs to know the air pressure, and then we have to know in space where it occurs, if it's closer to the nozzle or further away. And we use that to come up with our adjusted pressure at applanation to subtract, and we subtract BIOP to come up with our load of that cornea at applanation. So to interpret them, and this is probably the most important slide, this is how you interpret them. SPA1 and SPHC, the higher the value, the stiffer the response. And the reason is because if it's more resistant to deformation, if it's stiffer, it's more resistant to deformation, there's a smaller displacement. And that displacement is in the denominator, which means that the higher the value, the stiffer the response. But on DA ratio and integrated inverse radius, it's the opposite, because those you're looking at shape parameters, and a smaller change means it's more resistant to deformation and is stiffer. So with DA ratio and integrated inverse radius, smaller is stiffer. Stiffness parameters, higher is stiffer. So the most sensitive parameters to changes in stiffness, independent of IOP, relatively independent of IOP, are the integrated inverse radius, DA ratio, and stiffness parameter. And you'll hear more about all of these parameters in the subsequent talks. And the reason that I tell you that, that things are very sensitive is because when extra procedures were developed where very short cross-linking was done on top of a refractive surgery, I didn't believe it actually stiffened the cornea, because you can't go from a 30-minute applying of the drug to 30 seconds. 30 minutes to 30 seconds and actually accomplish anything. So I was very, very skeptical. But what happened is, first of all, BJ, who's here in the front row, did a model that showed you could stiffen a small layer without changing the outcome. And David Kang in Seoul, Korea actually did two groups of surface ablation, one with this very short, I think his was 90 seconds, 90-second cross-linking procedure, and then no cross-linking. And when he compared the two, there was a significant difference in both integrated inverse radius and DA ratio between the two groups. So these two parameters were able to show that the cross-linking procedure weakened the cornea less. They both weakened the cornea. Don't ever let anybody tell you that cross-linking will regain pre-op strength, because it won't. But cross-linking with these data weakens the cornea less. So that gives me confidence in the extra procedure, as well as tremendous confidence in these parameters that are put out that tell us about corneal biomechanics. So you'll hear more about really advanced techniques to actually detect at-risk corneas prior to surgery, because as you know, in the literature, there's many topographic algorithms and tomographic algorithms that based on thin corneas, irregular curvatures, and posterior elevation anomalies. But post-LASIK ectasia has occurred with adequate corneal thickness, unremarkable curvature maps, and posterior elevation within normal limits. So what you'll have described is how the addition of these biomechanical parameters is really important in detecting these at-risk corneas. Because in keratoconus, and this is my hypothesis, but curvature, thickness, and elevation are secondary changes to biomechanical. So the first detectable change, I believe, is biomechanical. The ideal detection scheme is this one on the bottom, which Renato Ambrosio will tell you about, is the combination of tomographic and biomechanical indices, so that you can detect asymmetry in multiple areas, asymmetry in curvature, asymmetry in elevation, and add the biomechanics to that.